we want to talk now about stability and the concept of bifurcations. And a bifurcation is a qualitative change in the behavior of a system as a parameter is changed. What this means, at least in the simplest sense, which is what we're going to cover today, is fixed points that we saw when we were creating these models. What we'll see now is that as we change a parameter in our system, fixed points can be created or destroyed. So for instance, there could be 0 fixed points, turn a parameter, increase the value of some parameter, maybe it's temperature, maybe it's force, and all of a sudden a fixed point emerges, or vice versa, you have fixed points appearing, you change a parameter, and those fixed points disappear. And secondly, the stability of a fixed point can actually change as you vary your parameter. So something that might be stable initially could go from being to be unstable as you vary some parameter in your problem. So let me jot down some of these general definitions for you. So we're looking at qualitative changes in the behavior of your system as a parameter is changed. And the two things we're going to focus on is fixed points being created or destroyed, or fixed points changing stability. Okay, and we're going to look at the 3 canonical bifurcations that occur in one-dimensional systems. All right, the first is what is known as a saddle node bifurcation. I will say there is no, I've been in the field of structural stability and stability in general for almost my entire academic life, starting at the beginning of my PhD. And I've never seen any field that has, let's say, more terminology or less agreed upon terminology for what they call these types of things. This might also be called a blue sky bifurcation, because fixed points appear out of blue sky as you change a parameter. So I'm going to use these terms loosely just because you talk to different people and there will be different things that they will call systems. However, the key thing is trying to understand kind of both the qualitative behavior of what's happening in your, say, in your equations as you vary a parameter, and also just looking and being able to identify the form of your equation. And that will allow you to kind of quickly ascertain whether or not you're expecting to see a certain instability appearing in your system. All right, so the typical, so a saddle node bifurcation is the kind of simplest example of fixed points being created or destroyed. And the simplest, or you might say the prototypical example, the simplest kind of equation that you can write down that would demonstrate this behavior looks like this. Let's see. f of x is going to be our x dot, which is going to be r. It really can be plus or minus x squared. We're going to focus on plus x squared for no reason other than it just changes the shape of your parabola. R is your parameter. This is whatever it is you can control in your system. So maybe you're shooting photons at something, turning up a temperature, turning up a load, whatever you can dream up, you're going to change the value of this parameter. And we're going to allow this parameter to be positive or negative. So it can be kind of any real number. And I think it's easiest to see that term, the blue sky bifurcation, by just simply plotting this function for different values of r. So what does that lead to? Well, we can look at plotting x dot versus x. And if we have a large value of r, so r is really large, then what you'll find is that this is going to be a parabola that looks something like that. Now here, x dot is above the line. So arrow is going to point that way. It's above the line. Arrow is going to point that way. It doesn't intersect with the x-axis. It doesn't intersect with another curve. It's simply a parabola in space. There are no fixed points. So when r is large, there's no fixed points. If we set r exactly equal to 0, what we see is the emergence of a fixed point at the origin. Now we can look graphically and see that we would expect things to move in this direction, and we would expect things to move in this direction. This makes that fixed point a little bit harder to define than normal, and it's what is referred to as a half stable fixed point. It's half stable because to the left of the curve, we have that negative slope. Remember, our linear stability analysis says that the slope of the derivative of your function dictates the stability. Negative slope means it's stable. Positive slope means it's unstable. So this half is stable. This half is unstable. And you can see that in the arrows too. You're kind of moving in this direction. But once you get here, you're going to be unstable. So you're not going to be, so you could kind of easily move away if you're perturbed. These are usually denoted with a half circle with the stable sides on the left. This is what's going to be the case when you have r is equal to 0. So you have one half stable fixed point. All right. And you can imagine what's going to happen. Really, all we're doing is we change r here, just thinking about the equations, is we're just lowering that parabola. And so we make r negative, our parabola goes down here. And now we clearly have two fixed points, so we can use this graphically to say, well, this one's going to go that way. This one's negative, so it's going to go to the left. So that means this has got to be a stable fixed point. This one's negative, so it's got to go to the left. And this one's positive, so it's got to go to the right above that side. And so this is going to be an unstable fixed point. Again, if you don't like the graphical method, you can just say, well, this slope is negative, so that's got to be a stable fixed point. This slope is positive, so that's got to be an unstable fixed point. So clearly here, we see that there are two fixed points no. When r is less than 0. So imagine this is kind of like a system where you're starting to turn a knob from a large gain, you know, maybe, or gain's not a good one, I don't know what negative gain would be, for some positive parameter, turning that parameter down, you hit 0, you go below 0, and now you have the emergence of two fixed points. One is stable, one is not. The bifurcation is said to occur when your parameter is equal to 0. The vector fields, or if you like, the qualitative behavior of your dynamical system is different when R is less than 0 as compared to when R is greater than 0. These are qualitatively different vector fields. One has kind of stable spots where it might find an orbit, and the other has no stable equilibria at all. Oftentimes, we don't really plot your bifurcation diagrams like this. What we plot them like is, since R is really our independent parameter in this problem, in a sense, that's the thing we're kind of changing. And what you often see people do is plot R on the x-axis, X on the y-axis, and then once we hit 0, let's see, we'll go green is stable, red is unstable. We have a stable fixed point when R is negative, and an unstable fixed point, or an unstable pathway, I guess I should say, when R is positive. This is the kind of simplest bifurcation you can encounter. I have good examples for the other two kind of canonical bifurcations. This one, I couldn't find a great mechanical example to give as a demonstration for like when you would encounter this one. I'll keep looking and see if I find one. I'll ping you all with an email. But the purpose of this thing is for you to kind of visually and conceptually understand that typically in an experiment or in some physical system, what you're doing is you have some parameter that's changing and you're trying to observe, is there some qualitative difference in the response of your system as you change that parameter? And here we see that different stable or unstable equilibria will appear kind of out of the blue when your parameter crosses a particular threshold.
Can I ask a quick question?
Yeah, of course.
If we're looking at, so for that last graph, if we're looking at when R is negative and positive, shouldn't that curve be like rotated and flipped? Right now it's like when X is negative and positive.
Yeah, so the way I would reinterpret this curve is to say there are no there's no kind of fixed points at all when R is positive. And then R at 0 leads to a bifurcation in your system's phenomena. And then at that point, two things can happen. If X is negative, so here's X, if X is negative, you'll tend towards that stable equilibrium. And that's what this is saying. So this is negative X. So this is stable. And if X is positive, you'll have this unstable pathway here, which corresponds to this unstable equilibrium point. I know it's a confusing diagram since we kind of flipped like two things at once and replaced the variable, but it's, you know, this is negative X and this is stable. This is negative X and this is stable. Does that help?
Yeah, that makes sense now. Thanks.
Yeah, no, well, I think maybe the confusion is like the plus or minus in our f of x.
I'm plotting this all for plus, yeah. I should have not done, yeah. So this is really, let me write this down. So this is all, yeah, sorry, thank you. So this is really, I'm plotting kind of f of it. No, let's do it over here. So all of these systems are for f of x equals r plus x squared. And then if you had this thing the other way around, it would all be flipped. So the parabola would be upside down. You'd be kind of moving it in a different direction. But yeah, so this is all for when we have the plus there. But I do agree that like this is a confusing way to think of it. It'll be less confusing, I think, when we get to instabilities that are more familiar to us as engineers. But yeah, so hopefully that starts to help. One of the things that I think is important for you to realize is that you often don't just like end up with like this equation that you're modeling. You end up with something usually that's far more complex. But the way you can kind of conceptually think about it is there may be points in your complex model where the system sort of looks parabolic. What do I mean by that? For instance, we could look at an equation that doesn't look like this at all. So let's look at an equation that's x dot is equal to r minus x minus e to the negative x. So this doesn't look like anything that's familiar to us in the kind of canonical form of a saddle node bifurcation. But look, again, kind of what we can do when we have an equation here that's got this complicated exponential term in here is we could consider doing a Taylor series expansion about x is equal to 0. Why do we care about doing it around x is equal to 0? Does that seem arbitrary? Kind of, but if you think about it, it's not, right? Because what we're saying is that if I look at this equation, the fixed points will occur at f of x is equal to 0. So when does this thing cross the x-axis? When is x, when is your kind of function here crossing 0? And so you're essentially kind of honing into a particular region. Now you could do this at any point. You could do this at like x minus a and observe, for instance, the stability around a particular location in your system that you're interested in. We're going to pick that location just to be 0, just to see. But you're going to find out that the behavior is qualitatively the same. What do I mean? All right. So what I mean is, okay, let's do a Taylor series expansion of this entire equation. And what you'll find is that if we expand this equation, kind of approximate it out around x is equal to 0, then we'll get something that looks like this. X dot is equal to r minus x minus our series expansion of that exponential term, which is 1 minus x plus x squared over 2 factorial plus more things. Now we can do a little bit of rearranging here, but you can pretty quickly see that the x's are going to cancel out. This is a negative x, this is a negative of a negative x. And we clearly see the emergence of an x squared term in here. If we simplify this equation, we get something that looks like this. I'm writing oops, I don't need that at all, do I? Sorry. We get something that looks like r minus 1 minus x squared over 2 plus some other terms. So this has the same algebraic form as this up here. It's r. Now r is shifted a little bit. You're changing the parameter plus an x squared. And here you have r shifted minus a x squared. This parabola would be upside down, but nonetheless, it's locally looking parabolic, which means there's some region as you play with your parameter space where fixed points will create or be created or destroyed in that process. In fact, you can actually generally define the kind of general or normal form for a saddle node bifurcation by just considering a generic function for x dot around the bifurcation point. So let me show you what that means. So this might be called a normal form. But we could just say, well, x dot is really not just a function of x. It's actually a function of x and our parameter. And the bifurcation will occur at the fixed point. When x is equal to x star at some critical value of your parameter. We'll call that R critical, RC. Now in the example we gave above, RC was equal to 0. That was the point at which we had observed the bifurcation. But of course, this could be shifted given the nature of your problem. And this idea of doing a Taylor series expansion of your function allows us to write down the generic form of this thing really quickly. What does that mean? What does that look like? Here's what it looks like. Well, we can series expand f of x of r. And what you'll get is, if you're expanding around the fixed point, then your point that you're expanding around will be at f of x of RC plus, this is just the Taylor series expansion. This is all I'm doing. I'm saying I'm going to do the Taylor series expansion about x star. So about the fixed point, derivative of f with respect to x. And this is going to be evaluated at x star. It's not a star. And RC. And we're actually doing a Taylor series expansion around 2 variables, which is obviously the emergence of r minus RC times the derivative of f with respect to r. Again, evaluate at the same point. One more term. And the same thing. Okay, this looks like a mess. It's just a Taylor series expansion when you have 2 variables. What are we doing the series expansion about? We're doing the series expansion about those 2 variables at the bifurcation point. The bifurcation point occurs at x is equal to x star. Here, x star is occurring, like, say, over here or over here. Well, I guess in the case of the bifurcation, it's occurring at 0. RC is the value of the parameter and when there is a bifurcation. So here, the value of the parameter when there's an bifurcation is, of course, r is equal to 0. And so we're doing a Taylor series expansion about x star and RC. So the first term is just the function at that point. And now we have to handle what on earth is going on over here. So let me see what's going on over here. Well, you'll recall that what we were doing before when we were doing our perturbation methods is we were saying, well, let's take something like this term here. And instead of carrying all those derivatives around, we can just simply say, we'll call this thing like x naught. And let's look at the second derivative here. And we'll say this is some prefactor. We'll call it x1. This is exactly the way we were handling our series expansion for the general solution for our perturbation methods. Now we have to handle this term here. This is the trickiest. So I'm going to come back to it in a second. This term is simpler in the sense that the function at the bifurcation point has to be 0. That's your crossing, you know, you're saying if I plug in the fixed point, then I should be at 0 here. So this thing should go away. And indeed it does. Now, what do we do with this brown term here? Orange term, I guess. It's a little trickier. And it's trickier because so far we've looked at a really simple bifurcation in which our curve comes down, intersects with the x-axis, and we say, okay, there's our fixed point. We could also examine a situation that corresponds to the intersection of, for instance, let's see here, let me write this thing out. So what if we said like f of x equals x dot equals r minus x minus e to the negative x. This is the example we gave. We can kind of plot both of these as lines. So that yellow is a bad color. Well, I'll do that in a second. So if we plot both of these as lines, then we could say, well, I'll have one line that's going to be r minus x. And I'll have a second line that's going to be my e to the minus x. Oh, that's terrible. And the bifurcation will occur when those two curves touch each other. When those two curves touch each other, another way to say that is they're tangent to each other, right? The r minus x is tangent to the e to the minus x curve. That tangency is a way of saying that the derivative of f with respect to x is equal to 0. And if you notice, the term that I highlighted in orange is the df dx term here. So this term fixed points if curves intersect tangentially. Meaning that df dx, oh, that's terrible. There we go. Equals 0. So this term goes away as well. All of this hard work was just to show that by thinking about the way fixed points can form and thinking about just taking a general Taylor series about an arbitrary function tells us that a saddle node bifurcation should have this form. X dot is equal to x naught times r minus r naught plus x1 times x minus x star squared. And if you look up, that's exactly the form that we have in our kind of generic simple form here up here. And then it's also allows us to determine that this is going to be saddle node instability by calculating x naught and x1, which are just derivatives of that function with respect to either r or x. This is probably sufficiently confusing, and if you're kind of lost at this point, here's the takeaway. A saddle node bifurcation for a 1D system, you have some arbitrary crazy function. Some point in that function, if it looks parabolic, it'll have a saddle node bifurcation. Meaning, if I drew some arbitrary function, so maybe I draw something like this, where I have here's my x and x star, I'm sorry, x dot. I could have some crazy function that is like that. And I could say, well, what happens if I lower, this is for some r, what happens if I lower my parameter and my curve? Let's see if I can do this. Sweet. See if I lower that thing, I'll just kind of color over it. So changing R, what you see is that there'll be the emergence of these fixed points here and here. And the way you can interpret this is that locally, this thing sort of looks like a parabola. And therefore, qualitatively, what you would expect is your system is going to change behavior as you change the control parameter in your problem. Saddle node bifurcation is one of the three canonical bifurcations, and it is the simplest way that you can write down an equation that will lead to fixed points being created or destroyed. Questions? Yeah.
I'm assuming that this could be expanded to either having more than one parameter or higher dimensions.
Yes.
Maybe it would become more complicated, but
Yes.
again, it's just a Taylor series expansion, basically.
Yeah. So the question was, hey, we're looking at 1D systems. Like there could be more than one control parameter. There could be more than one degree of freedom. Yes. And you can kind of just add complexity to your systems as you go. And the forms and the sensitivities to those parameters are what lead to, in the dynamical systems world, maybe the emergence of chaos in your system, in which there is a sensitivity to initial conditions that takes a deterministic system and leads it to a variety of different outcomes. In the structural mechanics world, what it can mean is that additional degrees of freedom and different types of sensitivities to loading parameters can lead to different outcomes. So what I mean by that is, for instance, we're going to talk about another type of bifurcation, which is the one that's kind of canonical for demonstrating Euler buckling. And it's a different type of bifurcation. It's known as like a pitchfork bifurcation. And in that system, you could add an imperfection in there. That would be another kind of parameter. You know, so an imperfection would be, you got a bar, maybe your bar is a little bit tilted actually. That's another parameter in your problem. So now you could change the load, and you can also change how perfect is your system. And then you could say, well, how stable is your system as I change my load? And then how stable is my system as I change my imperfection? And some systems are fine. Euler buckling doesn't really care. Imperfection, if you went in the home and did a terrible job with a beam and put some force on it and tried to measure the buckling force, you'd probably get kind of close to what you would expect from theory. One of the biggest conundrums of the 20th century was the fact that that same approach failed horribly with cylindrical shells and spherical shells under pressure, where if you take a spherical shell and you pressurize it and you say, when's it going to buckle? You can do the math. It's very hard. You can do the math and you'll find a solution. And you'll do an experiment and it will be way off. Like it'll buckle 80% lower than the load that it says it's going to do. And in that case, it's the fact that if you have an imperfection in your system, the imperfection parameter changes the stability of the system dramatically, and kind of destabilizes that shell. So you kind of have these two parameters, one being the pressure on the shell, the second being the imperfections in the shell, and both of them can change like the stability of your problem. And you can say, well, if I just look at the pressure, I can calculate when my system will go unstable, but I'm ignoring the imperfections, and they're actually really important. So your question, I can interpret it as like, this can get more complicated, right? Yes, it can. And they can interact. Sometimes that more complicated thing can be simplified, and you can ignore some stuff and say, a beam is a 3D system. Let's pretend it's 1D. It could have an imperfection in it, but that makes it harder. Let's pretend it's perfect. And you can do the math, and you'll get pretty close. And sometimes you can do that and say, a shell, it's symmetric. It's kind of like an arch if I just rotated that arch like this way. And let's pretend it's perfect. And let's figure out when it's going to undergo a bifurcation. And you'll be completely wrong. And so, yeah, it gets more complicated, but it's usually because of what you're neglecting. I'll say it that way. But yeah, if you're an optimistic person, I guess you could say the phenomena get richer as you add more degrees of freedom and more control parameters in your problem. But that also gets more difficult. Let's go to a different one, because I feel like the saddle node bifurcation, I don't have a great way to ground you physically with it, but I think this next one I should be able to. And the second kind of canonical bifurcation is what's known as the transcritical bifurcation. I don't want to underline it, it doesn't match. Okay. Transcritical bifurcation. If the saddle node bifurcation is the simplest way to demonstrate a system that can have fixed points appear out of nowhere as you change a parameter, the transcritical bifurcation is the simplest system that can demonstrate that a fixed point can change its stability as you vary a problem. Fixed points, so in this case, for instance, a fixed point always exists for all values of a parameter. And at least one of these fixed points can never be destroyed. We've already done a system that demonstrates transcritical bifurcation, although we didn't talk about it. And that is in the population growth, right? In the population growth, we use a logistic model, and no matter what value we choose for the carrying capacity of the system, that was that K parameter we chose last class, no matter what value we chose, there's always a fixed point that's unstable at n is equal to 0. No matter what, no matter if you have a system that has a huge carrying capacity and really you could just grow exponentially forever, or really small carrying capacity in which the system will kind of be out of resources really quickly, no matter what, once you get down towards 0, there's a fixed point there at the population of n equals 0. However, in the population growth example, obviously, it doesn't really have any meaning to have a negative population. So we couldn't look at the entire phase space, and we couldn't say, well, what happens if we let some of these parameters be positive or negative? If we look at like the normal form or the simplest form of the transcritical bifurcation, so I'm going to just write this, which changes stability. If we look at the normal form for a transcritical bifurcation, we get that f of x is equal to x dot, which would be r times x minus x squared. Here's the key difference. It's the appearance of x, which is our kind of 1 degree of freedom, being multiplied by our control parameter. And that changes things dramatically. First off, let me show you that our, the system we looked at last class is an example of this. So let's look at the logistic equation for population growth. And it looks like n dot, this is in your notes from last class, is equal to Rn times 1 minus n over k, where k is your carrying capacity. You can map these two equations together if you just replace n with x, and you would get x dot is equal to Rx times 1 minus x over k. And let's just be extremely clear, Rx minus Rx squared over k. So you can see the appearance of x in both of the terms. The logistic equation is an example of a system that would have a transcritical bifurcation. Except it doesn't, because we don't allow the population to go negative, because it doesn't have any meaning. But it's the same form. If our parameter number of organisms could be negative, then we would expect it to go through a bifurcation. Don't worry, we'll do a demonstration of one of these with a physical system in just a second. Okay, so let's see what this looks like. We know all right, so we know, again, we're going to plot the same idea. We're going to go and just plot. Oh no. Oh no. Barely. All right, cool. So when r is greater than 0, we get the population growth curve that we plotted last time. And that looks something like this. I didn't plot it in the negative last time, but we'll plot it there this time. And it looks something like this. Now we can draw our vectors on here and say, well, okay, here it's going that way. Here it's going that way. So this point's got to be stable. It's exactly what we did last class. And here it's going that way. So this point's got to be unstable. Oops. Now, if we turn R being equal to 0, what's going to happen in this equation is it doesn't move the curve up or down. It's going to move the curve kind of to the left or to the right. I guess maybe a little bit of both, really. Here again, our bifurcation is set up so that it occurs at the parameter being equal to 0. And again, we see the appearance of what's called a half stable state. Our negative slope is on the right here this time. So that half of it will be stable. Let me zoom in and draw that. Which you can interpret the half stable state to mean is that, like, if you started over here, you'll tend to this direction and you'll stay here. But if ever perturbed, you'll move away from it. All right, and if we make this thing bigger, we just get the opposite of the first curve. And now you'll notice that the opposite of this first curve means that this is our vector is going to go that way. Our vector is going to go to the right here. So this point is now unstable. And this point is stable. The key takeaway, the thing I want you to look at with this graph is not really the curves at all, although they're important. It is what is happening to the fixed point at the origin. So look here, when R is large, that fixed point at the origin is unstable. As R decreases, you see that fixed point doesn't move. It changes its stability. This becomes kind of this half stable point here. This is the point at which there is a bifurcation. And then as we decrease R further, we see that the point at the origin switched from being unstable to being stable. So in a transcritical bifurcation, that one of the fixed points is there always, and it undergoes a change of stability. We don't see fixed points appearing or disappearing. What you might say is that fixed points exchange stability after bifurcation. So let's look at the kind of the typical bifurcation plot, just like we did up here. We'll plot, not purple, I want to do black. Again, we'll plot our control parameter on the x-axis and our independent variable on the y-axis, or our variable x. And I want to do this. What did we say? We said green was stable. All right, so let's do green, and let's make this thing thick. So that means when R is negative, that fixed point is positive. I'm sorry, is stable. And then once our changes, we see a kind of exchange in that stability. This will be easier when I plot all of it together. So this curve here is stable, and this curve here is unstable. again, I understand this can be difficult to interpret. Here's how to think of it. There's an example. I'll give it to you qualitatively first, and then maybe we'll have a minute and I'll walk you through it. Kind of the most classic, simple, very oversimplified example of a transcritical bifurcation is for solid state lasers. Solid state laser, you take some matrix, some material, you put half reflective mirrors on each side of it, and then you just pump it excite it with energy. So you excite that material with energy. And then the atoms in that matrix are just going to start getting excited from their ground state and kind of moving around. What's going to happen anytime you're exciting atoms is that they're going to kind of radiate photons. They're going to give off light. So what happens in the case of a solid state laser is that as you pump in a small amount of energy, these things all bounce around excitedly, but completely random in terms of their phase and completely independent of each other. So you might have atoms over here vibrating a certain way, over here vibrating a certain way, acting completely independent of each other. Now you're turning up the power, turning up the intensity of the excitation of that system. And what's happening is it's just kind of sitting there glowing like a light, like a typical lamp. And then at some critical threshold, what you see happen is those atoms that are being excited independent of one another start to oscillate in phase with each other and all start to emit the same coherent radiation. And they're giving off these photons. They're not giving them off independently now, which is leading to kind of like white light. They're giving off a coherent radiation because they're oscillating together. They're kind of all excited past their critical point together. And that leads to the propagation of coherent light or a laser coming out of one of the sides of this material. So you have this scenario where as you add more and more energy into your system, you have something that's acting like a lamp, kind of doing nothing. It's stable, it's happy, it's doing that. And then all of a sudden it becomes easier and more, once they start oscillating all together, the the behavior of the system changes from them kind of all giving off random photons in different directions to a coherently phased light in which you see the emergence of a laser light forming past a certain threshold. Let me see if I can walk us through that example with some math. That's the qualitative behavior. It's stable when your parameter is low. It just doesn't do anything. You have all these kind of independently oscillating things. And then at some critical point, everything oscillates together in phase, and you see the emission of laser light. And you really have exchanged stability for it's harder for those atoms to oscillate independent of each other. Now they're going to oscillate all together. You can develop a simple model for this, and you can see the math drop right out of it. So let's do that real quick. Let's look at the model for a solid state laser. The model for a solid state laser, so I'm going to put some math behind the words I was just saying. So you're going to have something where you can keep track of the number of photons in your laser field. So the number of photons in the laser field, we'll call it N of T. And the rate of change of the number of photons is going to be N dot, so exactly what we want, something that's going to be kind of the dynamics of the system. The rate of change of the number of photons in the laser field is going to just be equal to the difference, the number that is gained versus the number that is lost. How are you gaining and how are you losing photons? Well, you're pumping some in, so that's how you're gaining them. So mathematically, what you're doing is you're saying you're going to send in some photons into the system. There's some gain coefficient that's determined by your material. So as you send photons in there, how much of that is actually used to excite atoms in the matrix. And then, well, of course, we want to know the number of excited atoms in the matrix. Let me write all these things down. So this is a gain coefficient. It's a material property. We already defined little n, so we should define big N as the number of excited atoms. Okay, well, then how are we losing things? We're losing some because some of these photons are going to escape through the mirrors. I haven't drawn the picture yet, so let me draw the picture so it's a little bit more clear. And what's K? Well, K is essentially related to the lifetime of a photon. So it's helpful for us to know that everything, that we can, in our system has some sort of characteristic scale. So a photon has a characteristic lifetime, tau, and the rate is going to be the inverse of that characteristic lifetime. The details are not too important, but it's just basically a difference between how many photons are being gained versus how many are being lost. Let me draw the picture of what this looks like. What the picture of this looks like is you have some partially reflective mirror. You have some solid state matrix and another partially reflected mirror. And what you're doing is you're pumping in energy to excite this. So they call it pump or excite. This is your active material. These hashed things here are your mirrors. And at some point, this solid state laser, oh, that's the wrong color, will start to emit laser light. So this is one part of our model. And there's one more ingredient that our model needs, which is that the number of excited atoms is not constant. It's going to be dictated by how much energy you're pumping in versus how much are kind of dropping back down to their unexcited state. So it's kind of like, I don't know, I think about it like billiards. You have these billiard balls in there, you hit something, you throw a billiard ball on your table, it's going to hit some billiard balls, knock them out of their ground state, they're going to start moving around, and eventually they might slow down and stop. So we're going to make sure that we have some kind of amount, the number of excited atoms. So we're going to keep that, keep a certain number of excited atoms in there. So that's kind of like your intensity of the energy you're pumping into your system. And then you have to account for the fact that some of those atoms are going to be decaying back to their ground state. So they don't stay excited forever. You excite some atoms, they bounce around a little bit like a billiards ball table, and eventually they decay back down to their ground state. So you insert this into this. And what we end up with is that n dot is equal to G times n times n naught minus alpha little n minus Kn. And just for the sake of putting things in the form that will be clear to us, we could write this like G n naught minus K times little n minus alpha G times n squared. You'll notice that these are your material parameters. One is kind of saying how well is your material absorbing the energy that you're pumping in, and alpha is saying once you've excited these atoms, how quickly are they decaying back to their ground state. And then you'll notice that the control parameter is over here. Which is saying you're going to kind of try to fix the amount of atoms that are in their excited state at n naught for any given time. But the takeaway is you have your control parameter times n and take away n squared. And if we just go look back up here, we see the same type of form here. Control parameter times your thing minus your thing squared. So we're going to expect this system will undergo a bifurcation. So what does this look like? Well, it looks exactly like how I was drawing things before. In that what you'll have is, let's see if I can draw this, is that if I'm plotting this for when the number of atoms that you're keeping in an excited state is lower than the rate that they're decaying back compared to how easy it is to amplify the system, then you end up with this curve here, which you can interpret as no laser. It's just a lamp. Everything is just kind of lighting up and glowing and everything, and that's fine, but it's not a laser. You continue to excite this up to the laser threshold, which is when n naught is equal to K over G. It doesn't look that different, except that by that critical point, that fixed point, now becomes half stable. And any energy input into the system above this value leads to laser light. And you'll notice the key feature of this transcritical behavior, which is that that fixed point at the origin undergoes an exchange of stability. It goes from being stable to being unstable, and the stable situation corresponds to the emission of laser light. This actually works fairly well. It doesn't take into effect all the kind of quantum mechanical behaviors that are happening that set these rates constants here. But if you actually were to plot real data for, as you vary the amount of energy you're pumping in, and you kind of measure the amount of photons that are coming out, and what you'll see is that your real data kind of looks like something like that. And your model is saying that it's going to be like, oops. It's going to be like this. Oh, come on. And then there's an exchange of stability that occurs and goes up like that. And this is happening at a value of K over G. You can vary G, so vary the material in your that you're pumping this thing into, and see how this curve evolves for different energies that you're pumping in. And so physically in the lab, what you're doing is you've got this material, you're pumping in some energy into it, and then all of a sudden, as you keep pumping more and more in, boom, you start to see a laser light form. It goes from kind of radiating like a lamp to shooting out photons like a laser. And the nature of this behavior is bifurcation, and it's a particular bifurcation in which the fixed point around there being no laser light is stable until you hit a threshold, and then it's no longer stable, and then the number of photons changes. Questions on this second kind of canonical form? I want you to keep in mind that it's qualitatively different. We didn't change the number of fixed points. Well, I guess in this case, you kind of do, but the key thing is we're not we can't destroy that fixed point at the origin. It's always there, no matter what value you choose for your parameter space. There will always be that fixed point at the origin. What happens in this case is that the stability of that fixed point at the origin changes, and that change of stability you can qualitatively interpret for this example as number of photons that are acting like a laser is basically 0 until it's turned on, and then it's not 0, and that happens when you cross a certain threshold.
So the turned on laser is still stable, quote unquote.
Mm-hmm.
So in a sense, this entire principle is changing our definition of stability based on the state of the system, or changing our relative definition of state of stability.
I think I don't know about that. I would say the system can't continue to not emit as a laser because that state is stable, so everything has to move away from that state. It's kind of like it's almost like it's almost like somehow the pendulum case, like if somehow this becomes a stable state because you change something. And so our definition of stability didn't change. It's still, you look at your curves, it's still.
Or I guess what I'm saying is, even though our emitted intensity is suddenly changing, our something else that we've defined is still stable in this case. Our excitation is still stable. With the green curve.
Yeah, I think I follow. Yeah. So that green curve is kind of like the green curve kind of goes from it's stable doing nothing, then it's stable having n be greater than 0.
Yeah.
But before that point, n being greater than 0 is unstable.
Mm-hmm.
All right, I have one more I wanted to show you. If for no other reason, then it's the one that's probably most familiar to you, and that is the pitchfork bifurcation. And pitchfork bifurcations are really important in mechanics. Because they're common in physical problems that have some symmetry to them. So think about a system that might have left-right symmetry, where it doesn't really matter. There's no energetic difference between your bar buckling to the left versus your bar buckling to the right. It's kind of, they're the same. It's just there's a symmetry to that system. And in these systems, because of that symmetry, fixed points appear and disappear in pairs. What is difficult about these systems is there's 2 types. I shouldn't use 1 there, should I? I should use, we'll pretend that's an I. One is supercritical, and the second is subcritical. The first one's easier and has more common examples to interpret, so we'll start there. So the supercritical case has the canonical form of x dot equals r times x minus x cubed. I said that these systems occur because, sorry, I said that pitchfork bifurcations occur in physical problems that have left-right symmetry, which you can interpret to mean you'll see the same behavior in your system if you replace x with negative x. That's kind of your left-right, the right being positive, the left being negative. If I put in negative x into this equation here, I get the same equation back. That's the mathematical kind of appearance of that left-right symmetry. And you could say that this is invariant if we replace x with negative x. This system, as you vary your parameter, takes on a very different look. So you have something that's going to, let's see here. Behave like this when r is really small, in which your vector field kind of looks like this, and everything's going to move to the right, and there's nothing that's going to change. It's just going to keep kind of deforming. You could think of this, if we want to go with the Euler buckling case, it's going to be the case of you're compressing your bar, and you're just continuing to compress it. You're loading it, and it's just kind of shortening. At some point, that fixed point at the origin, so what am I looking at here? This is x dot, this is x, that fixed point at the origin starts to really flatten out. This has the effect mathematically of, we said, think about stability, and we thought about linear stability, and we said, you linearize around the fixed point here, this kind of point's always stable. You linearize around the fixed point, I think that's half stable. If you linearize around the fixed point, then, actually, no, it's always stable, sorry. If you linearize out the fixed point, linear stability analysis tells us that we would expect a slight perturbation around that fixed point to either decay exponentially or grow exponentially. What happens in these pitchfork bifurcations is the critical point, it's stable at that critical point, but perturbations no longer decay exponentially fast. There's actually what's referred to as a critical slowing down as you approach that fixed point. There's been recent literature in the dynamics of snapping structures and buckling structures that show this kind of critical slowing down behavior, showing that kind of as you make smaller and smaller changes in the loading, that it's harder and harder for this thing to kind of decay back to its stable state. Okay, this is the critical point here, but let's look at what happens as we keep going. And as we keep going, we see that as we increase R further, we see the emergence of a pair of stable fixed points. And now that initial fixed point that we had is no longer stable. So in a way, this kind of combines elements of both the saddle node and the transcritical, because there's that fixed point at the center, which is always there. It doesn't get created or destroyed, but it changes stability. And now there's the creation of two fixed points. They come in a pair away from that origin. So it's in a way similar to what we observed is kind of combining both the saddle node and the transcritical, because we have an exchange of stability here and the appearance of two stable fixed points away from that origin. This is represented with the following diagram. Come on. If we plot this in our kind of bifurcation diagram, where R is the free independent parameter, and we put X on our y-axis there, and we come plot this, what we'll find is that when R is really small, up to some point at which R hits the bifurcation point, we see the appearance of two pathways. And then there's this additional path here that's now unstable. So again, this is easy to think about in the context of a buckling beam, where if here you have a beam that you're loading, and here you have a beam that, let's see, well, this would be positive to the right, so we'll say it would buckle like that. Here it would buckle like that. In this case here, the red curve here would be like if we just kind of had it stay straight, but got like a little shorter. So again, this now is stable. This is stable. And maintaining that initial path is unstable. This has analogies to second order phase transitions in physics. So it's often referred to as kind of a soft or stable, soft or stable instability, meaning it's, as you're increasing your loading parameter, once you get to this critical point, the change in behavior is qualitatively different, but it's not a dramatic, large increase in your, say, deformation of your structure. The opposite is true for a subcritical instability. Subcritical has a different form, which looks like this: Rx plus x cubed. And let me draw the bifurcation diagram for this one here. So the key difference between these two sub bifurcations is that this negative x squared term here, x cubed term here, is basically acting to stabilize the structure. And once it becomes positive, it's now destabilizing the structure. That's hard to see. The bifurcation diagram here also looks like a pitchfork, but it's kind of confusing. This one confused me for years, because what happens is, as you change R, it's stable, 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 stable. You get to the critical point, and now it's unstable to continue going this way. But also, it's unstable to go on these paths. And I found this befuddling. I didn't understand what was happening here. And So this is an unstable fixed point. This is typically kind of deemed a catastrophic instability and has analogies to first order phase transitions. And the reason I found this confusing is I always thought, well, what happens when you get to the critical point? You have this thing that's like stable, you get to this critical point, and what does it do? There's no stable pathways. And the answer is you have to look to higher order in your model. And there's something that we neglected that is going to stabilize the system at a higher order. What does that mean? Oops, that's wrong. It means that in reality, our system is going to have the appearance of a term, for instance, like Rx plus x cubed minus x to the fifth. Now, what happened to x to the fourth? Well, we said our system was symmetric about left and right, so all the even numbered terms are going to go away. And so what will appear is this kind of higher order odd term. This seems like a subtle change, saying that this thing is stabilized by a higher order term. But the result makes a bit, at least makes it make more physical sense, which is as we vary R, if we say this is R critical, and this is whatever X, and the result here is that our system will go up to this critical point. This path is now off limits. This path is off limits. This path is off limits. But the appearance of that x to the fifth term means that there's some other path over here that will appear to stabilize it. In physical representation, what this means, which is kind of cool, is that your system, once it gets here, is going to jump to this stable point up here. So it's going to have a really large change in its behavior to find that new critical point. This is analogous to, but not exactly the same as, the snapping of an arch. So I think I brought one. I don't know. Actually, this will work. Here, Post-it notes. You know, this is not exactly the same as, but this will give you a physical representation. This has a slightly different form. But if you take something like this, you load it to a point. Oh, I couldn't hold it. And it'll jump down to that next state there, where this stable state is pretty far from the last stable state up here. I'm trying not to move my fingers. Yeah. It's pretty far from that last stable state. And what that often means, and you can see it in the equation here, is that if I get to this point and I unload, then I'll go back over here. These types of instabilities have a hysteresis to them. They kind of switch back and forth. You go beyond that point with the critical load parameter, and as you unload to a different point before you go back. These are the bad instabilities. These are catastrophic, hard instabilities where there's a really large change in your physical qualitative behavior as you're loading it. I wanted to show you how to simplify the buckling problem so that you can see that it looks like an equation of this form, but I don't think I have time to do that. So apologies. Questions on the Pitchfork bifurcation?
Why did you introduce the higher order term again from the x squared to the subcritical?
How did I introduce it?
Yeah, how did you go from Rx plus x squared to?
That's actually x cubed, but basically it's, I basically just said there has to be one there. And that sounds kind of crazy, but it's one of the like the main like fundamental kind of lemmas of stability theory, which is that if you get to a bifurcation point, there has to be another stable place to go to. The only way a stable place could appear is if you have some sort of stabilizing term in your equation. X to the fourth is out because of the symmetry of the system. X to the fifth is the next available one. If it's a positive x to the fifth, that's not stabilizing. We need something that's going to kind of bring it back to where we are. That's that negative sign. And so that's like the simplest way that it could be stabilized. It doesn't mean it will be stabilized by x to the fifth. I guess it could be stabilized by a x to the seventh term or something. But it's this idea that if you, this subcritical bifurcation has to have some other stabilizing component to it. It just was neglected, you know, when you kind of first look at the problem. And so it's almost like if you arrive at something like this, then you have to go back and say, okay, my model is missing my higher order terms. I can find the stability, I can find the critical point by not including the higher order terms, but I can't tell you what it's going to do when I get to the critical point. All right, sorry, we kind of went really a couple minutes late. Are there any questions that you want to ask here, or we can always ask them during office hours? All right, thanks everyone.